what's unusual about this setup?
They're both arteries.
They're both arteries, yeah. Normally you have an arterial leads to a capillary, and then capillaries lead you back to a venual, right? Do you recall from our Chapter 19 studies, what happens to the pressure as you go from arterial to capillaries to venual?
It goes way down.
It drops. It really decreases. What does it allow to take place at the venous end or venual end? Reabsorption. This is one place we do not want reabsorption occurring. So to keep the pressure high, instead of having a venual lead, we have an arterial lead, and that maintains the pressure high enough in your capillary set. So what is not going to happen as we lead this glomerulus through the efferent arteriole? Yeah, no reabsorption here, because we do not want to reabsorb what we're going to filter out at these capillaries. So that's why we maintain high pressure here, is to force the fluids out of the capillary and keep them out until we decide what we want to reclaim back. So kind of an unusual setup here. Alright, so let's hit the bullet points on the top of page 114. The only place filtration occurs in the kidney is in the glomerulus of your nephron. We also call the glomerulus the glomerular capillaries. And what we do now is we form filtrate. So I want to talk to you for a moment about what filtrate is. Think about blood for just a moment. Back from Chapter 17, blood contains blood cells like red, white, and platelets. What else is found in blood? Plasma, good. So what's in plasma? Protein, a lot of liquid or water, dissolved stuff like what? Yeah, sodium, solutes, potassium, glucose. Even waste products are found dissolved in the plasma. So the plasma is kind of like a catch-all river where items are dumped. So what we're really interested in filtering here is mainly the plasma. We're not really interested in taking the blood cells out for filtration. So red blood cells, white blood cells, and platelets are not going to be removed through the filtration process. But blood plasma, minus the proteins, will be removed from the bloodstream due to the process of filtration, which is pushing that fluid across the walls of these capillaries. Keep in mind, we've got to have high enough pressure here to push this stuff out, capture in the Bowman's capsule or glomerular capsule, and then we can start doing whatever it is we want to do with that filtrate. So you'll notice there, what should not be in the filtrate are items that are too large to pass out of the capillary. That includes the red blood cells, white blood cells, and blood proteins. We don't really need platelets to travel out there either, because unless you've got damage, you really don't need platelets to go. Here's the problem. If you filter out something like a red blood cell, the red blood cell is going to be too big for reabsorption down the road. So if you filter out a red blood cell because you've got really high blood pressure, then unfortunately it's going to be lost in your urine. It cannot be reclaimed back into the bloodstream. So red blood cells, white blood cells, platelets, and plasma proteins are going to continue doing their job in the bloodstream. They travel through the glomerulus on a courtesy tour here, keep on through your efferent arteriole, and then they travel back through the blood system just like, nothing happened. So when you're thinking about the blood flow here, you're going to have to link the efferent arteriole back up to those, what? Where does efferent arteriole take you?
Peritubular capillaries.
Peritubular capillaries. Boy, that's weird, isn't it? Arteriole, capillaries. Another arteriole, and then that takes you over to another set of capillaries. Those peritubular capillaries take the red and white blood cells eventually back to a venule, and that venule hooks you into what vein?
Renal.
Ultimately the renal, exactly. So that's really where those red blood cells, white blood cells, platelets, and plasma proteins go. All they're doing is going for a tour through the nephron. They stay in the bloodstream. They're not filtered out. The only case of having white blood cells get out would be what kind of situation?
Getting rid of infection.
Yeah, exactly. Getting rid of an infection. So you're not going to have those white blood cells removed unless they're moving by diaphoresis, which means they walk across the walls of the capillaries and head to the area of infection. But under normal conditions where you don't have an infection to fight, they'll just continue riding in the bloodstream as well. Okay, so here's a little review for you from back chapter 16. You'll notice the next bullet point says in italics, this is the fourth bullet point down, under what conditions will filtrate form. Okay, so that's page 114, fourth bullet point down. You have to have normal blood pressure, systemic blood pressure, to form the filtrate. If your blood pressure is too low, then we have to work to increase the blood pressure. Do you recall the name of those special cells located near your glomerulus that produce angiotensin? We talked briefly about them last class period. JG, good. The juxtaglomerular apparatus, we call it the JG or JGA for short. If your blood pressure is too low, the little cells actually sit kind of in a triangle shape right in here. What they do is they start secreting angiotensin. Angiotensin constricts the efferent arterioles. Is the efferent arteriole the one leading away from or into our glomerulus? Away from. Traditionally, this would have been a venule, right? And traditionally, this meant the blood pressure would drop. So, what will it do to the glomerulus pressure if you all of a sudden constrict the efferent arteriole pressure? It'll increase it. It'll make it easier for us to filter out the blood plasma rather than letting the pressure tend to drop just a tad as it travels into that neighboring arteriole. So, interesting how we have a little set of cells there called the JGA. Their job is to secrete angiotensin. Like the name implies, angiotensin means we're going to constrict the blood vessel leading away from the glomerulus, making filtration still be able to continue. You might recall from way back when in chapter 16, we talked about aldosterone. What does aldosterone do? Good. Helps to increase, maintain sodium and water, and it does increase blood pressure. So, you've got a short-term fix here with the JGA, constricting the efferent arteriole for angiotensin, but you've also got a longer-term mechanism here because notice that angiotensin promotes the formation of aldosterone. And if aldosterone helps to retain sodium and water, you've got a long-term fix for getting more fluid in the plasma. And what does that ultimately do to your blood pressure? Increases it. So that's what we're looking to do here, is we're doing a short-term fix with angiotensin too. We're doing a long-term fix, though, with that aldosterone hormone. Okay, so down below, you notice we have NFP, which is net filtration pressure. NFP is simply the amount of pressure that has to be present to push fluids out. Where are we pushing fluids out? The afferent arteriole, glomerulus, or efferent arteriole? Glomerulus. Good. So the glomerulus is the site of filtration. So what is filtration? Push water out, yeah. Push water and any solute that can fit through those walls of the capillaries out. What we're having to do here is make sure that we have high enough pressure to push out so that none of it is reclaimed back. We don't want to reclaim any back for reabsorption just yet. We need for these solutes and fluids to travel down through the rest of the renal tubule. That's where we'll do the reclamation or reabsorption process. Alright, so hydrostatic pressure and osmotic pressure, those are old friends for us from back in chapter 19. Which one of those is pushing fluids out?
Hydrostatic.
Hydrostatic. Which one is trying to pull fluids back in?
Osmotic.
Osmotic. So which one has to be higher to successfully perform filtration? Hydrostatic, yes. So as long as hydrostatic exceeds osmotic pressure, then you're going to get filtration to occur, and that means you push fluids across the wall of the capillary. So notice the net filtration pressure here. Under it where it says colloid osmotic pressure, the NFP it says is approximately 10 millimeters of mercury. boy, that's not very big at all, is it? That's a real tiny pressure, but that's all we need to be able to form that filtrate. What if somebody has high blood pressure, such as hypertension? What do you think hypertension does to that number?